All right, Christopher, how are you doing?
I'm good. Thanks, Aaron.
All right, are you ready to present?
I am. I will just click on the slideshow and
All
hide
right.
that.
Well, what I'm going to go ahead and do here is I think I'm going to hide and let you talk a little bit about your stream processing engine, and maybe Gregorius and I will pop in. Would it be better if we popped in at the very end with questions?
As you see fit. We'll see how it
Okay.
goes.
In that case, what I'll go ahead and do is I'll hide us, and maybe we'll pop in like a genie and go ahead and ask questions periodically.
Okay.
Sound good? All right.
Right. Well, many thanks for that. My name's Christopher Rowe. I've been a contract programmer since the mid '90s, most for about half my adult life. And since the sort of mid 2000s, I've been working in the manufacturing stroke power stroke water industries. And so the project which I'm going to be talking about is sort of motivated by my experience in those sectors. And most of the time that I've been working there, I've been working in what's called the data historian technology, which basically captures real-time data and stores it. It's fairly simple data structures. We've got a timestamp and a value, and it mostly sort of sensor data, sort of temperatures, flows, and things like that. But I have had exposure to quite a wide variety of programming languages. I started off mostly in web development, moved into Erlang Elixir, and in the last 10 years became quite interested in functional programming, which I don't do as my day job. But in terms of the functional programming, I started off, if you can call Erlang and Elixir functional, I started off there and then had some closure work and taught myself a bit of Haskell. But for the last few years, I've been using F# predominantly. I came to .NET through, I came to Akka.NET through my experience with Erlang and Elixir. I wanted something that could use the actor model, and it was something that I could do from F#. Just a quick word on my data historian technologies, what they do. Basically, as I mentioned, they capture time series data from sensors in near real time. And then they add, the main job that they've got to do is to basically store that data, to write it to disk eventually. But they will also add some sort of utilities like visualization tools, and they can contextualize the data. A lot of the data coming in from the sensors will have no context, i.e. you don't know it's come from this pump or from which part of the plant is using that pump, for example. So they add contextual level of data, so that this flow data and this pressure data come from the same pump, and they're situated in a particular part of the site. And they also provide a mechanism for adding calculations, adding two flows together. What I'm calling here finite state machine. As you can see on the right here, this is a blocks of time slice data. The blue is some sort of healthy state, and the red some sort of unhealthy state. And you basically got a swim lane chart there of when a particular reading comes in or out of specification. And they also do things like batch data, which is basically to do with the process of manufacturing data according to a recipe. And then they can send out notifications when certain things are finished or when things are too hot or whatever. What characterizes a lot of these data historians is that they're complete turnkey solutions, i.e. they offer everything from visualization tools to contextualization and calculation engines, etc. I also did a fair bit of work in manufacturing execution systems. Basically, they are mechanisms for describing how the processes involved in manufacturing a particular product. You can see a particular flow chart here, and that basically might say add water into a bowl and then add some chemical, And so each of these lines here defines an operation, and in each operation there may be more than one phase to that operation, and the phases might get executed in sequence, or they might get executed all at the same time, or there might be some condition to them. And those rules are expressed in recipes. And at various points, the recipe has to hand over control to a particular machine that can, for example, read the pressure and check that it's within bounds. And this orange sort of level layer is a bit of technology that can talk to the instrumentation here on the right and bring results back to the recipe controller. And so those are the two kind of motivations in terms of my career, which have driven this particular project. And I started working in this area during lockdown, where for whatever reason I was unable to. I didn't have work on, so I gave myself a number of challenges, and this was one of them. And basically, the initial challenge was to say what would be involved in taking a function. And this particular function here has got 3 parameters. They're all essentially floating point parameters. They're wrapped up in this time series data structure. Basically, it's got a timestamp and it's got a value. And in this particular case, it's just simply adding those 3 numbers together. But in terms of getting the data streams out of a real-time database, there would be 3 streams of data, 3 separate streams of data, and they would all come from a particular data source, and each parameter then would take its own flow. And so my challenge myself was, how would I construct a function and then pipe through different streams of values through that function? And so here on the bottom here, it's emitted as a new stream. What I should say from the outset is that in terms of my use of Akka.Net, I only used a very small percentage of the surface area that Akka.Net offers. These are the packages that I included. And for the initial project that I gave myself, I didn't even need Akka.Remote here. But these, so as I say, this is small scale in terms of the usage of Akka. But I'll come on to how it became a fairly significant part of the project that I did. But in terms of actually solving this particular problem, so basically each of these icons here represents an actor. So there's an actor that can listen to a particular data source and then can get other actors to subscribe to that data source. And this actor here represents a buffer, and the reason it's a buffer that can be controlled with a tap that turns on and off the flow. And the reason why I need that is that some of these data streams may be late arriving, so that if I want to add up flow from this pump and flow from that pump and flow from this pump, the 3 data sources may be out of sync with each other, sometimes by a few seconds, but it could be also by hours even. And so I need to be able to wait until the next bit of data comes before I execute the function. And so I need to be able to turn on and off the flows as they come into the function before they execute. And the process of taking of data from an emitter, I call these basically these broadcasters. They emit the data. The first thing that needs to happen is that they need to be unpacked. They could be encrypted between the data source and the data processing center. And then, as I mentioned, I buffer them in some particular form. And this tap here represents a release strategy. I might want to batch it in 5-minute windows or hand them out one by one. And then they come in to the transform function, which is the function I've just been describing here, where the 3 flows are added together. And then whatever data is output, it gets dispatched normally to another emitter like that.
So
So
a
go ahead.
question for your sort of approach here. So
Yeah.
it looks to me like what you're essentially doing is leveraging the location transparency of actors to some extent to be able to go ahead and have these little functions that look like they're kind of aggregating over and buffering data from potentially multiple streams, and they themselves can be composed together into another function that someone else can use further downstream, right?
Yeah, absolutely. So I'll come. Yes, if you're indeed. And
I'm
some of the
sorry, I'll let you
slides.
get.
No, not at all, not
Yeah.
at all. So one of the features in that initial solution was partial function application. So this, if I'm going to collect data over a period of time, this function might take a float and two integers and return a float. So this function will take the first float, and that will result then in a function that takes two integers. And when that integer finally arrives, that it gets moved on to the next buffer, which takes the last integer and produces a float, and that float then becomes the emitted data. So I'm using functions as data stores. There are other ways of doing it, but this allows me to have different data types coming into the same store, as it were, and also to incrementally over time gather them. So I basically, that was my initial challenge. I had some other additional things that I wanted to be able to do. I wanted to be able to take historical data and treat it as a stream for backfilling and testing purposes. And I also wanted to be able to isolate the transform functions from all the infrastructure that Akka.Net provides for messaging and for the buffering of data, so that if I wrote a function like this and saved it to disk, perhaps copied it into a folder, then the system would open it up, create all the infrastructure that was required, and register the function with some discovery node, and that other people would use it. And so this then, as Aaron was pointing out, is where the collaborative, borderless software as a service type idea comes in, so that whatever the size of your universe, whether it is global or whether it's within a particular company, different people can collaborate and basically submit a function to a central library, and then anybody can then compose those functions. And so this particular function here, they've got a fetch function which basically gets the data from a particular source, and as Aaron points out, location transparency is a big feature here. And then the next process, I can smooth the data, analyze it, and then possibly visualize it. So that became the broader objective. So what the way that I've sort of borrowed from functional programming here a little bit. This is just simply a data structure here. It's not a function, but I treat it as a function. So this might be a function defining multiply. Multiply takes two inputs. In this case, they're both floats, the left and the right hand side. And I'm going to output a float, and I might put in some options to basically to clamp the data. There might be a maximum value that I allow, let's say 100 or whatever. So this is the definition of a function. I would then advertise, I can do this, I can multiply, and this goes to the function library of what it's able to do. And if somebody then says, oh, that looks like an interesting function, I would like to have it, he sends a message over to the provider over here, who will then deploy a proxy that represents that service into the actor system that the function that the composer would use, and then I can then supply the information about where to get the data from. In this particular case, go to server X and use tag A, and server X tag B, and use those streams to produce the output. So essentially, all function definitions, they describe some sort of processing capability, and all functions have a list of stream APIs as their inputs, and they may have some configurations, which is just basically a key value pair list. So this is the API that all the streams expose, that you can either subscribe to it or unsubscribe to it, or you can pause the stream or resume it. Underneath that, the stream will have obviously a way of injecting data into the stream, but that's not visible in the public API. Data sources have 0 inputs, but use config to identify specific metrics such as the tag name identifying a particular stream of data. Data syncs will have at least one stream input, is what data do you want to save or output, and they will also produce output streams, but typically metadata describing whether the operation was successful or not, how many writes per second are taking place. And data transforms have at least one input and produce a single output streams. So, for example, if you're adding 2 numbers, there'll be 2 inputs and 1 output. And here is a fetch data definition. This has no inputs, and it has it specifies in its options the name of this is the definition of the function. And when somebody uses that function, they say, okay, I want tag A from this particular provider, and each provider might provide more than one function. This is basically a function providing floats, so each data type will have its own kind of function. So if you wanted to return strings or something like that, that would be a different function. So what we've just seen is using specific tag streams as inputs into a function, but you can also use other functions as inputs to So in this particular case, I'm filling the left and right hand side of a function that multiplies 2 numbers with another function, which is multiply, and a function which is add, which basically gives me a function of takes 4 floats, 1, 2, 3, 4, and produces a float. And this is how I might call it. I might say, well, go get your data from server X and use tags A, B, C, and D. And that would basically represent A times B times C times plus D. So here we've got function definitions as arguments. So you can grow your function definition simply by splicing in new functions into old. And in this particular case, I'm applying 3 functions to this. Here's the function definition that has 2 functions. So basically it takes 4 floats. But in this particular definition, I'm only supplying 3, which leaves what I call a hole. So the function is not completely specified. So it remains simply a functional definition. Whereas in this case, the new function definition is a function that takes a single float and produces a float, which is the D parameter is missing. So it becomes a function that's just simply waiting for that final value in order to actually start processing data. In terms of the kind of architecture, the guy that's supplying the data or the service has what I call a provider, which advertises its services. So it will publish a list of what it can do to a function library, and it is, when it's asked, it can initiate the deployment of the proxy, and it does that through a proxy manager. The proxy manager does the actual deployment of the proxy actor, which is the representative of the service locally. And when the data actually starts streaming, there's a sort of a separate channel. So it's basically one wave flow. So that was a scenario where the service is the supply of data. So it basically produces data. And here is a service that I can encrypt the data. That's going to consume the data. So the flow is the other way, unless, of course, you can make the decision that the service is deployed the remote site or to the client site, in which case the work will be done here. There are some caveats around that in terms of the size of the code that will do will provide the services, to whether you can deploy it, and that there are some other constraints in terms of the classes and the data structures that you need to do the encryption need to be accessible on both sides of the wire. So in terms of the project that I've been doing, everything services are remotely deployed. I also, as I said, I've got the facility to export a DLL and to have the DLL read. And by executable here, you might actually just start a completely new actor, and that's got its own set of services. And then something that I haven't explored yet is actually using the F# compiler to pipe down code and have it compiled remotely. So as I mentioned, there are certain considerations in terms of sending functionality over to the client side, the size, security, and what deployment mechanism you're going to use. The function definitions I've shown you before were sort of simplified a little bit, but this is what the definitions look like in code. Basically, if anything's unresolved, it remains an abstract function. And so what can be unresolved is a stream input, and this is basically expecting a stream of floats. But they may also require some configuration details of these key value pairs. And again, if that's required and it's not provided, it represents a hole. And until all the holes are filled, it remains a function definition as opposed to an actual stream. And here, basically, the streams are resolved, and this information here defines where the data is going to come from. In this particular case, it's coming from file. The QFN and the initials stand for qualified function name. So basically, the function name will have a data source, where it's getting its data from, and a function name. So that's a resolved function definition. So one of the challenges that I had when sort of doing this is that if I've got a function request, and that function request is composition of two elements, one is to fetch data and one is to find active periods. By active period, I mean that between these squiggly bits where the data values shoot up, there's a lot of low values, and these low values where let's say you've got a suction pump that's running and it's only periodically on, there might be quite large gaps in between the active data, and so there might be a function that identifies what those are. But given that function, I've got two functions here. One is to fetch data and one is to find active periods. They might have been advertised and are known about in what I call the discovery node, but not yet actually deployed. And so if somebody wants to use them, then this deployment process has to start. For each undeployed stream builder, we have to ask the provider. The provider will set up a proxy manager who will then deploy the proxy actor, and then the proxy actor will tell this function library, this is where you can find the actor that will build the infrastructure that you need in order to execute that, to create a stream API out of these two functions. Now, that's a process that can go wrong. It doesn't always work. And the quotation here is from, is from A.A. Milne, who has a poem called The King's Breakfast, in which the king wants some butter. He asks the queen for some, and she asks the dairymaid, and the dairymaid asks the cow, and the cow says no. And that leads into sort of a semi-diplomatic crisis. and which is fortunately resolved happily for the king, but it takes some negotiation. And so it's reminiscent of the ACTA process, that messages get passed from one place to another, and all of those transactions have to work. And so we've got what I call a discontinuous process, and that needs managing. And so I've got what I call a recipe runner, and so this is it's effectively a little bit like this diagram here, where you've got operations, and each operation has got a number of phases, and running through all of these is what I call, well, there's some sort of document, and that document will describe all of the inputs that are needed in order for each operation to successfully run. So if a function has some input streams, that he knows where to go and find them, that'll be in the builder doc. And if the aim is for that document to be completed with the results of the new stream that's going to be put together as an aggregation of the old streams. And so each phase gets the builder doc. That will tell it what its inputs are, and eventually it will update that document with a result, and that result will if successful, will represent a new stream. But instead of actually supplying that stream the details, it supplies a function which I call an action here, and that function is a builder doc to builder doc. So basically, when the operation is complete, this document gets passed to all the phases, and so the recipe runner has now got, if I was looking at these three here, the recipe runner would have three functions, and after the operation is complete, those three functions will return to the recipe runner, which then gives it the builder doc for them to update, and they each update, and then that document now in its updated form can go on to the next operation layer. So
in your taxonomy here, what would be, let's say, a builder doc, like from a real world point of view, and what would be some like the functions that are actually being used to kind of achieve something here?
Here's an example of a builder doc. So a builder doc is any document that you want, and it's basically, so if you want to add 1 and 2 together, you would have those two numbers in there. Those would be your inputs, and so these fields that I've got here are kind of arbitrary, but they're what I need in order to put a Stream API together. So you'll see there's one parameter, one field called params, and that's a list of function param doc, and what that is it's basically got the provider of a function, a provider of data or a service, and that service has got some inputs, may have some inputs that it needs in order to fulfill your request, and so it will use that input to determine to build its Akka.Net infrastructure, and then supply you with the result. And when that result, when you finally get it, you'll put back into this document in the field output here. The form of that will be what I call a build infrastructure result. But basically, inside that structure is a Stream API. And it gets a little bit more complicated in the sense that I don't know ahead of time how many streams.
I lost your audio and video for a second there, Christopher.
Oh, right, okay. Am I back?
Okay, well, you're back. There we go.
So I was just describing the builder doc has got the inputs that are needed to create the streams. And the streams, when they're finally built, get put into the output of the document. And this structure here basically allows for the fact that I don't know ahead of time how many input streams I'm going to process. So there's a way that I have to find out from the container document, which in this case is the builder doc. I have to find out all of the parameters. In this case, is the function parameter doc, which I'm calling the child doc here. The command is how to build the stream, and then these two functions here basically tell me how to insert the data back into the original document, so each child document, and then that gets passed up into the to the parent document. So those were that was one of the so basically what that does is answer the question: when is this whole process finished? How do I know when I'm ready to supply the inputs into a function? I might have, if I'm adding 3 flows together, I might need 3 streams ready before I can do the function.
So it's kind of like a recursive sort of tree structure that, and each node, basically each node completes when all the different child tasks have written their output back to the parent, basically.
That's right, exactly it. Okay. Yeah.
Got it.
So in terms of the demo that I was going to run, what this code up here does is essentially pseudocode at the bottom. I've got a data provider which I call random, and it's sort of semi-random number generator. So I'm going to a provider called random, and I'm saying, give me your data for tag A and give me your data for tag B, and then pipe both of those into a function called math.add. It's going to add those 2 numbers together, and then finally, I want you to send it to a pub sub actor, and that actor is then going to basically make its data available over to a WebSocket. And if I stream here, so what I've got here, this represents what I call the discovery node, which is on the client side. If you've got somebody on the client side who wants to be able to compose functions, they will send their request to this discovery node. This discovery node already has some what I call builders, the builders that can build stream APIs together. There's one that smooths data. There's one that determines red, amber, green out of some configuration data, so if it's too hot, too cold. Here's the function math.add. So those are the functions that are already, there's one that can write a file. Those are the functions that are already registered with the discovery system. I've got one here called random. This is the guy that produces the random data. So this guy can produce data. Right. I was looking out for this message because basically now this guy has told the Discovery Center that I can produce random numbers. My provider name is called random, and I've got a function which I'm calling float because it produces floating data. What is my subsystem? So this is a website, and so the website is now running, and it sent a message over to the discovery system that says, I'm able to consume stream data and publish it across a pub subsystem. And this is going to be another actor here. This is just an actor so that I can interact with the system and send it. This will talk to the discovery node, and I've just basically set that up and running. And so basically what I've done is executed that the function which this was the function. Yeah, basically here I've asked to give me 2 random numbers. So I've asked it, give me 2 random numbers, add them together, and then send them to the pub subsystem. And that's what's going on here. This is where the random, this is the guy that's originating the data. It sends it over to the discovery system. The discovery system is then routing it onto the pub subsystem. And you can probably see this word discarding data at the moment. And the reason it says that is because nobody is signed up to the data. So we can change that. If I load a website and then subscribe to the data, and here we've got the squiggly line of happiness where the data is now streaming, so essentially from random through discovery, where it's getting added to the discovery has got this math.add function. It's transforming the data, and then it's sending it over to the pub subsystem, and from the pub subsystem I've got the data in my browser.
This is like a very location transparent version of Akka Streams that also has discovery built into it and the ability to kind of compose.
That's it.
In Akka Streams, we call it a graph. The ability to kind of compose graphs across multiple different nodes, and it's very basic. I can see the cogs turning here in my head. This is very cool. It's like a combination of a bit of a data mart functionality where you have data sources that are available, but also the ability to go ahead and even expose combinators for that data if you wanted to.
So one of the motivations is that some of the companies I've worked at are smaller than others, and some people have got the ability to have in-house teams of data scientists and things like that, but not everybody does. And so for the smaller energy companies, for example, they may want to buy in functionality like that. And so the idea is that you could have this collaborative approach to publishing, processing data functions. And if you need it, you either stream your data to where the functionality is, or stream it, or send the functionality down to where the data is. That's at least the concept. If I go back to the slide thing, I don't know how much time we've got left, but so that's up to the demonstration of the composition thing. What I was going to talk about now was just simply my experience of using Akka.Net. Just have a quick look at the time here.
You got plenty of time. No
right,
worries.
Okay. So the development experience for me was, the quote here is, "In the sunshine it's warm, but there has to be more." It comes from a poem in which the poet describes how marvelous life is and everything's going really well, but every stanza finishes with the line, "There has to be more." So even though things are going great, we'd like to have more. And so the sunshine of this for me is that only using a sort of a small footprint of the Akka.Net technology stack, I'm able to get a distributed system with location transparency, which is extensible. So one of the extensibilities that I want to be able to see is to add new functions and basically advertise them without having a monolithic application that you have to stop and start, and with fault tolerance built in, and the things to sort of actors to self-heal, to work out that they've come down, and to work out what the best way of resurrecting themselves would be. So the more that I would like is that at least, and I've worked in isolation here, and one of the disadvantages of that is that best practices may not be well known if you've got colleagues and things like that to pass on better practices. But for me, I've came across, I had a number of clashes with sending messages from actor A to actor B, not knowing ahead of time whether that message would get there, because of the typing clashes. So I would get a lot of undelivered messages. And again, coming from functional programming, I tried initially to pass functions across around the system, and a number of reasons why I wanted to do that, but it didn't. It doesn't work terribly well if you're not careful. Also, if I create an actor using Spawn, that the actor that I get immediately, and it says in the documentation that you should only use it locally. I ran into one or two headaches before I realized that that was what the problem was, that I was passing actor references across actor systems, and that didn't always go very well. And this is just, I've got a number of question marks here, which basically indicating that a lot of those things is stuff that I need to take responsibility for. But they're nevertheless part of my experience of using them. One of the things I'd like to do is in my business domain to remove the message mechanics from it. That my business domain shouldn't really know about tell or something like that. It should do a function and return data. And then in this whole concept of when you've got an actor, one of whose most important jobs is to pass on a message, which is a side effect. And basically, how do you test that that message is passed on? I ran into a couple of occasions that, at least on the F# Akka system, that if an error is thrown, that you get the message is silently processed. You don't know that the error has occurred. You just know that the side effect, i.e. writing to file, didn't work. I'm not sure how to debug distributed systems, and so I've got a lot of writing to console to see. And the King's Breakfast problem is what I describe as just basically if there was a negotiation process to had, so the king asked the queen, asked the dairymaid, asked the cow, how do you know that that's what your system is doing? Or is it through documentation? Or I would like to have some place where I can see that that's what my application is doing, and I've yet to work or to find a satisfactory solution for that. So this is basically just repeating myself a little bit. But so if I were to send a message, now there some of my data types are sort of slightly involved, where it says tag values in the example that we just seen about data going to a pub sub. The outer tag value is the name of the topic, and the inner tag value is the name of the tag. So that's just simply two labels wrapped around each other. So it's not terribly complicated, and inside there's a time series value of float. But if you don't get this typing just right, you can basically then get a dead letter. Now, I probably didn't help myself a little bit because I didn't allow in my message handling loop for unrecognized messages. I would insist on a particular data type. So when I had a function create Akka mailbox, you pass in a specific message type that is going to recognize, and the state that the definition of the data model that you're going to store state in. You pass those both in. It spawns an actor and gives you back the message handler for it. But if you don't, but it will only take of the data type that you send in, and if you get it slightly wrong, then you spend quite some time for figuring out why. So there are other ways of creating actors that you can get better feedback, so that here I've got basically I've got an unexpected message. I can at least print it out so that you've got some idea of where it came from. The dead letter messages will give you some idea, but here it tells me that the message is a pub sub message, but not which one. The pub sub message. In F# you can basically have subtypes of pub sub. It doesn't tell you which subtype of the pub sub message that failed. And I got this message a lot. Failed to deserialize. That's because I was passing functions around across system boundaries and across DLL spaces. And if one side doesn't know about the data structure of the other, it can complain. And then it might take some time to work out which bit of data structure it doesn't recognize. Now, so one of the reasons why I like using functions is that if I've got a callback ID, so coming back to, or this whole process, if this is a process where I have to go through a number of loops, and eventually the person that asked for that stream API needs to be told, here it is. So I will then store a stream ID and put it into a dictionary with the callback, and then but what I don't want to have to do is to pass that ID around everywhere. But if I send in a function that's already got the callback baked in, and then I just simply tell the system, or tell the other end, just put your data here. So it doesn't know about this callback ID, because it gets a function that just simply wants data, and that's allows me not to muddy the business domain on the other side. That said, and the other thing that I want to do is to be able to limit the surface area of an API, so that if my API accepts payload, I don't want that exposed to consumers. So I will basically create a function that only allows them to pass in a stream API message, which I then map to the internal structure and then forward it to the relevant actor. I could create completely separate actors, which basically pass-throughs, but that's slightly clumsy. Now, that all said, I'm slightly going off the idea of function passing, and so might look at constructing functions at the other in a sort of intermediary stage, what I'm calling here the target controller, the data, the endpoint that gets the message. That could possibly construct a function and pass it on to the business logic later. So, and this basically, I ran this a couple of times, again, passing out to references across systems. Doesn't really like it. And these are kind of more notes. A lot of these are notes to self as to what I would like to focus on next. Basically, how do I test side effects if the main job of an actor is to send a message? How do I know that it was sent? How do I test it? And I've talked about all of those other things already. One of the things that is in progress is that if data is late arriving, I may need to send an interim result. I mean, that if it's going to be in the water industry in particular, data can take some days to arrive, and management might want an estimated value in the meantime. So you need a strategy for saying, well, let's use a substitute value for the moment and then recalculate later. So as data comes in, there'll be an orchestration layer that will determine we've waited long enough, so use this value in the meantime. And the other features of the Streamline, which is where basically they're not Akka.Remote related, which is basically be able to define functions, not in terms of the tag names, but in terms of some description. That there is an asset model which gives tags a description. So in this case here, we've got, if I can find my mouse, inlet volumetric flow rate, and then I might use that inlet volumetric flow rate as the description when defining a function. And I might want to apply a function across a data model, so use this function. So here's basically is a function which I'm called percent in outflow, and it has two parameters, and I want to apply that across, let's say, all water tanks in the enterprise or in the plant. So it would then basically search a whole data model and then create those functions, at which point it would do what we've already just seen in terms of creating the infrastructure needed for Akka.Net, etc. So stuff I haven't really worked on yet is, how this distributed system, how it's going to resurrect itself if it falls over, and what systems can generate. At the moment, I've typed in equations and things like that, and that would generate infrastructure, but whether you could automate that whole process. By contract driven, one of the features of the data historians that I've worked on in the past, if the system falls over and then restarts, there's no guarantee that the calculations which you have asked it to do will be done. That's a feature that should be reasonably easy to build in. And I think that pretty much brings me to the end of the presentation. Thanks very much for listening.
Well, Chris, I thought your presentation, and I'll bring Gregorius back here. I thought your presentation was fantastic and extremely detailed. And some of the feedback from some of the members of the audience, they really liked your section where you talked about where you struggled with Akka.Net to some extent. Mm-hmm. And I had some thoughts on that myself that I wanted to reflect upon, but you're on a roll. so I let you finish. My first thought on some of the challenges you ran into, I have two. First is that the typed, I just got done talking this morning to one of our longtime Akka.Net users who's used it at a couple different companies now. And one of the things I was talking to him about was Akka.Net 2.0, which is not the next big release we're going to do, but the one after that, which is all about typed actor references, where essentially you describe like an interface here, like all messages that belong to this interface or an F#, this discriminated union are what this actor ref can process. And you wouldn't even be able to you'd get a compilation error rather than a dead letter or a silent message. That should eliminate many categories of issues you ran into as far as that goes. Things like function serialization, I'm not sure we'll ever do all that well. We're almost somewhat constrained by what things like FS Pickler can do behind the scenes, but it also makes me think that the F#, the Akkaling library is out there for being able to go ahead and do some typed actor references in F# today, and being able to go ahead and have sort of a more idiomatic F# look and feel, but it's not really the official Akka.Net F# API. I'm thinking that I've had it on my sort of in mind for a while that's something that we should probably fix in the Akka.Net F# sort of experience, just kind of tidying that up and giving users something that feels a lot more native. Right now, that the fact that those spawned actor references, it sounds like they don't serialize very well when they go across the wire. That's problematic. That's something that we should try to fix. So that was good feedback for me as well in terms of things that we should be looking forward to. So that was something that I really appreciated. Let's see who else we have on. Let's see, we've got Arjun. I showed this up a little bit earlier, but he said this feels like a dynamic Akka streams implementation where you can introduce new stream definitions at runtime. And I think I would say the biggest key innovation of your system. So streams has that same sort of type safety and composability, and it does in theory have the ability to work across process boundaries, but it's a little bit more how to put this, cantankerous is the word I'd use to describe it. What I thought was really innovative about your design was three things. First is the data mart aspect of it, the sort of service discovery capability for finding data sources. That's something that Akka Streams does not offer and probably won't for the foreseeable future. So that by itself is a super powerful function. And then the composability, which Akka Streams also has, but you have the ability to go ahead and compose partial functions and share those as well. Whereas there's this sort of like higher order dynamism to it. And then finally, the last thing that I really liked was the notion of sort of the ability to kind of have these sort of composable formulas that you can kind of share around and reuse, those sort of the little docs that you talked about. I thought that was a really nice way of being able to kind of like elide over a lot of the underlying implementation details. You can work at the level of functions, but you can also go ahead and build docs, and you can also go and compose those together as well. Where that's almost like composing streaming applications together, not just the components of streams themselves.
Yeah.
So I thought that was very innovative, all of that. Let's see, some other feedback for you. Thanks for the show and tell. Very thought-provoking. So you've definitely given us a lot of food for thought here. So in
Well,
terms of your next steps here, so are you planning on in terms of what you intend to do with your streaming engine, are you going to make this into a product that you try to sell to customers in the industries that you work with, or are you going to open source it, or what are some of the, what sort of future directions do you think you're going to take this in?
Well, that remains to be seen a little bit. I have shown it to sort of ex-colleagues of mine in the manufacturing sectors. Had one of the reasons I'm grateful for the opportunity to do a presentation. It's kind of focused my mind a little bit to answer questions just like that. So in short, I don't know the answer specifically, but I will be approaching what I call integration companies, the people that are going to put systems into manufacturing companies, and just see what kind of feedback I get. The product that I've got at the moment is what I would call a happy path product, i.e., and I mentioned earlier that I'm not using supervisors and things like that at the moment. To be production ready, it would need to be robust, and if something falls over. So there's actually quite a lot of work in making it production ready. So my main target is to kind of look for these integration companies that might be interested in doing that. I would also say that, I mean, it has started off as a personal project, and it became something that I woke up wanting to do, and that's what's kind of driven me on with it. But the next stage will be to have more conversations about it with people in the industry.
Sounds good. And we wish you luck with that. And one last thing I should mention is, you mentioned you've got to work on the fault tolerance, and you mentioned testing distributed systems as a weak point there. It occurs to me, so we have the multi-node test kit in Akka.net for being able to do things like inject failures into a distributed system. We also have a flavor of that for Akka.Persistence as well, being able to go ahead and simulate, like Akka.Persistence journal rejecting a write, that sort of thing. Those tools are all out there, and there's documentation on what they do and what the various components are. But it just occurred to me in your presentation, I've never put anything out there on like, what is the type of test you'd want to write with those tools? And how do you go about structuring, let's say, your pre and post conditions when you're a distributed system? And what do you want to look for as far as success or failure in those types of tests as well? So that's given me some more food for thought there. Yeah. Let's see. One last comment that came in here from user Roman. Let's see, there's a project called Lunatic that's very similar to Akka that runs on Rust that can compile WebAssembly, run it anywhere, so you can compile a graph of composed functions and send it over the network to execute it. Woo. Very cool. Doing that all inside the browser. That's kind of like Atwood's Law. Now, anything that can be run, anything that can be JavaScript will be JavaScript. Well, now we've got WebAssembly, which I guess is really the ultimate form of that. Well, Christopher, thank you very much for your time. We'll go ahead and reach out to you after we end the stream here and make sure that we send you some Akka.net t-shirts and other swag for your trouble. So thank you for your time. We really appreciate it. And once again, thank you to everyone who watched today. I guess, my bad, Gregorius. Before we conclude, I should have asked, do you have any questions or comments?
No, it's all a bit over my head. So, yeah.
All good. It's one of those things where I think you kind of have to. I'm probably going to have to digest this a little bit and go back and watch the presentation again at some point down the road myself. So you're not alone in that camp, Gregorius. Particularly with some of the F# niceties on there. The sort of functional way of composition is a little bit different than the object-oriented sort of stuff that we do every day in C#, obviously, right? All right. Well, Christopher, this was an amazing presentation. Thank you so much for your time.
Thanks for the opportunity.